Welcome back, my friends. Welcome to our next unit, or at least our next part of this big study of electricity and magnetism. They go really hand in hand. This is about, well, I guess we do get pretty quickly into electromagnetic interactions, or how electricity and magnetism um, can really almost cause each other. So first thing we talk about is what we call magnetostatics, I guess. Or if we just have a magnet sitting there, what does it do? All right, so let's say that we have a bar magnet here. And a bar magnet, magnets have what a lot of you know we call poles, north and south. Right now, a big misconception is that north is like positive and south is like negative or something like that. But that is absolutely not true. If we were to say put a electron right here and just put it there, it doesn't go anywhere. There's no force that a magnet exerts on that stationary charge. All right. There certainly are forces that magnets exert on moving charges, but that's in a few days. Actually, that's in a little while. So just big deal. North and south are not positive and negative. Magnets are not charges. So for now, let's just deal with magnets as they are. Now, to look at the field, the magnetic field around a bar magnet, what we can do in the lab is use a magnetic compass. All right, and one thing that I'll say off the bat is that magnetic compasses, point in the direction of B. Well, what's B? B is magnetic field. Yes, it's a vector because it has a certain strength and points in a certain direction. And who knows why it's called B? I couldn't tell you. So what I did do was I loaded up this applet. It's one of those PHET, physics and engineering technology, I don't know. One of these applets here that has a bar magnet in it, flip polarity, so it looks more like ours. So here's a bar magnet with a north and a south pole, and here's our magnetic compass. And when we say that compasses point in the direction of field lines, the business end of the compass, the red part here, points in the direction of the field line. So what we can do is use this compass and move it around in different places and look at what the field looks like. All right? And what I sometimes tell people to do is, if we just say, use this compass as an indicator, well, it says the field line points to about, like 1 o'clock. So move it in that direction. Well, now it says the field points kind of that way. Oop, now it says it points that way. Now it says it points that way. Now it says it points, well, that's as close as I can get to the magnet. But that leaves us, it looks like, with a field line that looks something like this. Okay? Now, wherever we put this compass, come here, compass, we can see, ooh, now here, or actually kind of anywhere near this south pole, it looks like, come here, it looks like the field points towards that south pole. Yeah? Got that? And over here, anywhere near the north pole, oh, of course, it looks like the field points away from the north pole. All right, so that's a general rule. And again, here's where it can get tricky and sort of remind you, or even confuse you maybe, that gee, it's just like just like electric fields. Well, there's an analogy, yes, but again, they're not the same thing. But it looks like in general, magnetic fields point away from north poles and toward south poles. All right, and we get this, again, as an analogy, not saying they're the same thing. This is kind of like the electric field between a positive and a negative. All right, we call this an electric dipole field. Well, this is called, the field around a bar magnet is called a magnetic dipole field. Okay, and they sort of look the same except for the fact that, well, you can never get a north without a south. All right, we can have just a plain old positive charge. I'll just leave just the plain old negative. So sure, we can have just a electric monopole, a single charge, and we know what the field around that looks like. It's a radial field that points inward all over the place. But if you take this magnet and cut it in half, you don't end up with just a north. All right, magnets are impossible to separate into monopoles. There are always both poles together. All right, and so for that reason, the fields are a little bit different. Let's go back here. Our magnetic field is going to look like this. Well, it points away from north poles, and I'll sort of say this comes back over here. It points away from north, towards south, and here we actually get something like this, like that, and this comes into here, and comes into here, and here we get something like this. Now I'm going to show you what the big difference is. The big difference is that these fields, and I should make this like a dotted line. These fields, the field lines never, the field lines never end. All right? Magnetic field lines are continuous. All right? So this one really keeps coming in here and comes through here and then comes back out to there. And these come in here and come through there and come back out, and so on and so on. All right? So I'll draw this one over here where we have like this, and then outside, and then it comes back around. Okay, so magnetic fields point, well, you kind of have to say it in two different places. Outside the magnet, they point north to south. All right, inside the magnet, they point south to north. All right, now, this means that something sort of weird happens. All right, how do you know how to get to Santa's house? Well, you get out your compass, right? And what does it do? Well, it points you towards north. But wait a minute, over here, oh yeah, and oh yeah, the Earth creates its own magnetic field. The strange thing is that outside the Earth, which is a magnet, or acts like a magnet, field lines point from north to south. But the compass, which points in the direction of field lines, points us towards Santa's house. So that should sound strange to you. So what it means is there's two different things. This is what we call, of course, geographic north. And this is what we call geographic south. But if the field points, leads us towards geographic north, and the fields point towards magnetic south poles, it means that this is a magnetic south. And this is a magnetic north. All right, so the Earth is a lot like a bar magnet. It has a field that looks, let me see if I can draw it. Well, it points like this, sort of coming from inside the Earth, and then outside it looks like this, where it swings up around like that, and in here it, again, swings up around like that, where these field lines, this is supposed to be like in front of the Earth. This is supposed to be in front of the Earth, right? The field lines point from magnetic north to magnetic south. So our geographic north, where, the North Pole, what we call it, is actually a magnetic south pole. All right, now this shows you something else also, why, I don't know if you've heard this, some of you I'm sure have, magnetic compasses don't work very well near the magnetic poles. And the reason is, look at the field lines. Near the poles, they actually point like into the Earth. All right, if you look, say here, over Baja, Mexico there, the field line points along the surface of the Earth, right? Or right here, we can see that better. The field line points along the surface of the Earth. But if you get up here, notice the field line's pointing down into the Earth. All right, so that's not going to help you, figure your way along the Earth's surface. That's why magnetic compasses have a real hard time working well at near magnetic poles. All right, so here's the big takeaway from this page. What do magnetic fields in general look like? Okay, now here's where we get into the interesting stuff, and it's about. We start here with why are things magnetic at all? All right, and what I'm telling you is everything has the makings of a magnet, and that's because everything magnetic, all magnetic effects come from moving charges. All right, when charges move, magnetic fields are created. All right, and so there's a simple. We'll start with maybe the most simple, what's called right-hand rule. We're going to get a whole ton of these, well, several of these, that talk about the directions of things, right? And so what we have here is a straight current-carrying wire. Here's our wire. And if we say that electric current, now notice, this is big deal, big deal. I is always for us conventional. Conventional current. Make sure you are comfortable with what conventional current means. Right? So the deal is this. The right-hand rule says if you want to know what the magnetic field around a straight current-carrying wire looks like, you take your thumb, here's your thumb, and you put it in the direction of the current, of conventional current. Step 2, you take your fingers and you wrap them around the wire. And your fingers wrap around the wire in the direction of the magnetic field. So that's what's indicated here. At any location, you have to look at what direction your fingers would be curling if you want to know the direction of the field. So there's 4 places we could talk about direction of the field. One is, well, let me do this. I'll call it position X and position Y. And then we also want to know in front of the paper, or sorry, in front of the wire. So that would be literally off the plane of the paper, like raised up off the front of the paper, or behind the wire. So that would be like, you know, again, off the paper, not in the plane of the paper, but behind the paper. Or in this case, the wire. So let's say that our conventional current, I, goes up. All right? This stinks, you can't see my hand, but if we wrap our hand, sorry, first put our thumb in the direction, I'm literally doing it right now like an idiot, you can't see me. You put your thumb in the direction of conventional current, so that your thumb points up. Imagine wrapping your fingers around the wire. Now, of course, you can't put your fingers through the page, but if you could, by the time your fingers are wrapped around a position X, which is in the plane of the page, the magnetic field, or your fingers, would point B is out of the page, out of page. Right? They would be curling right back towards you. Right? Conversely, at Y, again, thumbs upward, where your fingers are at position Y, your fingers would be trying to poke through the page. All right? So that means that B points into the page. Now, in front of the wire, again, thumb up, fingers wrap all the way around. If we wrap them till they come all the way in front of the wire, and you should be hopefully doing this with your right hand right now, your fingers should be pointing directly to your right. So B is right. Well, never mind, I'm just going to use an arrow. B is that way. And if you wrap your fingers behind the wire, right where they're behind the wire, your fingers, you know, if we really are looking kind of tangent to this circle, right, here's our circle over here, we're looking tangent to the circle back there, it points that way to the left. All right, so B is to the left. Okay? Okay. Now, that's near a straight wire. Now again, what we're trying to address here is this idea that all magnetic effects come from moving charges. So here's a case where we see moving charges create a magnetic field. All right, here's another case where moving charges can create magnetic field. And let's do this. Let's connect one of these terminals of the battery to that part of this loop, and this one to that part of the loop. So this is like this loop, the plane of the loop is perpendicular to the plane of the paper. Okay? And that's why I put this three-dimensional battery. So this is kind of like the front of the battery, which makes this sort of like the front of the loop. All right, the back of the battery is back there somewhere, and so here's the back of the loop. Now, let's label this, let's give it a certain polarity. Let's call this the positive terminal, and that the negative one. Okay? Well, here's the deal. We can still, if we want to know what the magnetic field near a loop of current, if we want to know what it looks like, we can still use our right-hand rule from the last page. All right, so if we look, say, right here, and that means, well, if positive is here in the front, that means that conventional current is going up like this and down the back. So we could still use our right hand, right? Put our thumb here in the front, put our thumb up, wrap our fingers around the wire, and two places we want to talk about the loop. All right, sorry, talk about the magnetic field. So inside the loop, we have a magnetic field. Well, right here, the magnetic field inside the loop would point to the left. All right, if we look, say, right here, again, thumb up, inside the loop, the magnetic field points to the left. If we do it up here, and now this is tough because here, your thumb points really into the page. Right? If you put your thumb into the page and wrap your fingers around that coil, again, inside the loop, B is going to point to the left. No matter where you do it, inside the loop, the magnetic field is going to point to the left. And then outside the loop, outside the loop, no matter where you do it, B is going to point to the right. So we get this magnetic field that looks like this. Inside the loop, it points like this. And then outside, so it still points like that. I'm just breaking that line to show that this is like gives us some it gives us some three-dimensionality, I guess, right? We go in front of this wire, and then we go behind that one. But then this loop, this magnetic field is going to curl around like that. It's going to curl around like that. Now you notice that field looks exactly like the magnetic field near a bar magnet. Whoops, a bar magnet. So that leads us to this. A loop of current can give us a magnetic field just like a bar magnet does. All right, loops of current. Well, there are, fill in the blank, I don't know what prefix goes in here, millions, billions, trillions, zillions of time. There are tons of these tiny little loops of current in everything. So what are these tiny little loops of current and everything? Well, they're orbiting electrons. So everything has bajillions of electrons that we can sort of model as moving in circular loops. All right? And circular loops of current create magnetic fields just like bar magnets do. All right? So everything has moving charges in it, and moving charges make magnetic fields. So therefore, everything has sort of the potential to act like a magnet. Now, before we leave this page, I do want to go back a step. So here's where we sort of did this by following our right-hand rule from the last page, right? Put your thumb in the direction of the current, wrap your fingers around the wire, and they'll point in the direction of the magnetic field. All right, the other way to do it is this. So, or, that's this. One, I'll say you can wrap fingers in the direction of conventional current. So in this case, my fingers would go up the front of the page here, up the front of the loop, and then down the back of the loop. Notice, if our thumb is pointing straight out, thumb points in the direction of magnetic field. Hugely important qualifier inside the loop. Okay, so hopefully you can do both, right? Here's the old way where we put our thumb in the direction of current and fingers wrap in the direction of magnetic field, but you have to do that at lots of different specific places on the loop. Here, we get to wrap our fingers all the way around in the direction of current, and our thumb points in the direction of magnetic field inside the loop. Okay? So I'll just add a couple of things there. Yep, sure, like this, like that, like that. Oh, now the other thing we should do with this was we should be able to label, right, if outside the magnet here, the field points away from here, right, and toward here, it means that this is really like our North Pole, and this is really like our South Pole. All right, so we have to be able to, again, tie direction of magnetic field back to kind of what polarity a magnet would have. Okay? Okay. So, real important thing here, right? That everything has tons and tons of little loops of current in them. So everything has the potential to be a magnet. So why isn't everything magnetic? Is kind of the next question. I'm looking for it. There it is. So what we can sort of simulate here is that, imagine we got a little loop of current like this, right? Well, and that thing makes a little magnetic field that, say, looks like that. Okay? And in a non-magnetic material, oh, okay, fine. Well, hang on, bear with me. Okay. In a non-magnetic material, what you can imagine is there are little electron loops that are in all sorts of different directions, all right? There's no order to the way they're oriented. So what you might get is, little what we call magnetic domains, that's what they're called, that point in all sorts of different directions. There's no order to the direction that they point in. So these are like having a bunch of little tiny bar magnets all oriented in random directions. All right, and what do they do, or what's the combined effect of all those different magnetic fields? The combined effect is nothing. All right, so a piece of wood sure has lots and lots of little tiny magnets in it, or things that act like little tiny magnets. But the fact that they're all sort of competing against each other, or at least the fact that we can, their vector sum literally is 0, makes the piece of wood not magnetic. But you get something that is magnetic, and what you have is something more like this. The magnetic moments point, I don't know if it's literally all in the same exact direction, but they really line up a lot better. So we get some combined effect of all those little magnetic domains. Okay? So that's the difference between things that are naturally magnetic and things that aren't. Right? Now, some common fields we need to be able to talk about are fields near the poles of magnets. Okay? Now we know that, again, this north doesn't occur by itself. It has a south pole that's off the screen somewhere. All right? We just don't see it. Same thing with this south pole here. It's got its corresponding north somewhere else. But in between these two poles, well, remember, magnetic fields point away from north poles and towards south. So here we get a field that combines those things. Away from north and towards south, we get this field. That should look familiar to you. It's not the same thing as that other field we talked about, which is an electric field, but it sure has the same structure, all right? And notice, of course, that those lines, those field lines, are all the same distance apart. They're all parallel, all right? And that tells you something very important about the field. All right, we're going to have to make sure we remember to talk about that when I see you next. Another example, this one here on the right, well, fields point away from north, so this field is going to, well, do this, right? Analogous to that field sort of between like two positive charges. right? Again, they're not the same thing. I'm not saying that, but they are pretty good models of each other. Okay? So first part of this unit is a lot of non-mathematical stuff, right? Literally, we'll take quizzes where all you do is use your right hand as the key to solving all the problems, right? So getting a hold on these right-hand rules right now, and the general definition of what direction magnetic fields point. That's the most important thing right now. Okay. Now I know I've never tried to teach this, obviously, without you guys being able to see me. So I understand. I totally understand if this is like really confusing with what direction my thumb or my fingers are pointing. So that'll certainly it'll help when you come and see me, come back to class. But I hope this was a good start. Okay. See you soon.